Okay, so hi everyone. Welcome to the second iteration of reverse engineering, and this time I'm going to talk about MTK for happy reversers or happy reverse engineers. I hope everybody can hear me. If not, well then. Oh, well, I think more is going to happen today than last time. Last time we were talking about Qualcomm emergency download mode, and this time we're going to have a small chat about, well, MTK, especially Bootrom and exploitation, and having a look at the MTK devices. Okay, so let's go. I'm giving a short, brief introduction into MTK. So having a look at how the MTK chipset actually is being used, it's just the same as for most smartphones. This time we're going to have a look at the Android devices. So over here you can see the secure boot chain. The secure boot chain starts with the Bootrom. The Bootrom is a fused ROM code. It's read-only. It's in the chipset. It cannot be changed. Can only be hot patched, but not as you think using rel code. And the Bootrom is going to identify the preloader. For that, you have keys which are being fused to the eFuses, means the public key, and the preloader has to be signed with the RSA public key. And in the preloader, a lot of things are going to happen. So the preloader isn't stored in the regular eMMC partitions. It's being stored in the boot 1 or boot 2. Most of the time, it's just in boot 1, and the other times it's like you've got a shadow copy in boot 1 as well, and boot 2 normally contains the serial numbers for the Wi-Fi and for the device itself. So in the preloader actually loads the trust zone and loads the UART, the hardware registers, the watchdogs, the meter mode, which is a special well, let's say research and development mode for the MTKs. And the preloader itself, it's going to start the little kernel or the UEFI, which is EDK2, and the little kernel has stuff like fast boot, as you know, and it loads boot and recovery and starts as well EL1 apps. And the little kernel then starts boot or recovery, and boot itself consists of kernel and RAM disk for the older Androids, and for the newer Androids it's just the kernel because the RAM disk is being stored in the system or in the vendor partition. And even if you look into the newest Androids, there's only a SUPO partition which contains the system, vendor, OEM partitions, and so on. And these are signed as well. So things to well, do your custom ROMs tend a bit to be more difficult these days than it was in the past. So speaking of security mechanisms, especially for the preloader and the Bootrom, we've got several. These are just a few that you've seen for sure. The first one is the typical secure boot chain, which means it's going to identify all following modules, which is like preloader, boot, and so on, using RSA public key. And DAA is the download agent authentication, and it means that only signed and authenticated DAA loaders are allowed, which is the case, for example, for those well nasty Hisense, Oppo, Xiaomi devices, whatever. SLA, that's serial link authentication, which means that you need to send a change response initialization or handshake for USB, and that's typically also done using an RSA key. And I haven't seen it very often being in use, but for example, I've seen it for the Alcatel phones. And last but not least is the root certificate, and I have no idea what that is, but it's also one of those security mechanisms. And what's not on that slide is you've got even more, which, for example, for the newer MTKs, you've got memory read, memory write protection, or EA command protection, and remote protection. Because for the newest MTKs, it's that if you use the SP Flash tool, it's going to remote connect to the server. It's going to ask, is that guy allowed to do any Flash interaction with that device? And if it says yes, then you can continue. So that's also another security mechanism. Okay, so let's have a look at what attacks actually we do have for the Bootrom. So thanks to XYZ, we've got quite some. The first one he developed for the Amazon Fire TV and the Fire TV sticks and the Echo was Ammonet. And in fact, it uses just GPU AES registers. It's not really an exploit. It's just a misuse of the AES hardware registers in order to use the memory pointer to override memory content. And if you then, for example, have the AES engine and you've got the proper writes, which is you're free for, of course, and then you've got a blacklist, which is going to identify which addresses and offsets and lengths you are allowed to read and write. And if you override the blacklist, actually you are able to modify the pointers and run your own code and read and write, of course, memory. And well, the problem with Ammonet is that the GPU AES isn't used for the newer devices. It has been used for the old devices. New devices use instead the DXCC, which is the ARM crypto core hardware engine, which works different. So you don't have a memory pointer for the AES algorithm. And well, that led to the next exploit that XYZ did, which is Kamakiri. So it's based on the Bootrom. It's a real exploit. It's based on the control handler in the USB stack, which means that you've got a buffer overflow, and you're able, if you know which area you are able to write, which is often called variable A or variable 1, then you can write your own data into a small leakage area, and in that leakage area you can also execute the code, and well, that's Kamakiri. It doesn't work for all MTK devices, but it works for like 90% of the MTK devices. And the last one is Hashimoto. It's my own one. And it's also not really an exploit. It's the same as Ammonet, but it uses instead the CQDMA registers to achieve just the same. So to override the blacklist and then allowing you to modify pointers and run your own code. So what about a generic exploit? So what you might know that Chaos Master, he's got a public repository, which is the MTK patch tools. It's called MTK bypass. I'm just writing it over here. You can find it easily on GitHub as well. It uses the Kamakiri, and when they did it, it's Chaos Master and Dino. They made some payloads, and they had to do a payload for each CPU. So when they started, they had like 3 or 4 payloads, and then I joined the crew, and then to go with Chaos Master, I had a look into more and more Bootroms, so we dumped as many smartphones as we could to get the Bootroms for any chipset, and then I decided to develop a generic payload, which means payload that isn't bound to the CPU, but it's automatically exploiting its way through, which means it works for almost any MTK actually. So and that payload actually it allows us to bypass SLA, DLA, DAA, SPC, memwrite, memread, all those nasty security protections. And honestly, the highest protection I've seen so far was on the vendor or the OEM HMD, which is known as Nokia or Foxconn. And I think the second in range would be the Oppo in terms of protection. So next slide. What about next slide? Yeah, here we go. Okay, so let's have a look at how the eMMC UFS read and write actually behaves. So if you're using the SP Flash tool, which most people do, it means that you normally land directly in the preloader. So that means that if the phone is powered off and you connect the phone, you will be in the preloader initialization, and from that you load download agent. And for the older devices, that would be enough. So then with the download agent, you could read and write. So the download agent actually has the functionality to read and write eMMC and UFS. And in the past, there has been just one download agent protocol. But then with newer devices and larger storage, the speed became very low. So they had to have something to accelerate the dumping, reading, and writing. And for that, actually, they made a special area in the preloader file, which is the DRAM in it. So it uses DRAM to accelerate the usage. And that's the reason why you, for the newer devices, need to have the preloader file in order to get the DRAM in it to make the download agent work. Without that, normally it shouldn't work. But I've seen some devices where it does. I don't know why that is, but I think it depends if you use a generic DRAM in it or if you have some special or custom memory in the smartphone. And well, so much for the preloader, but most phones can also be put into the Bootrom mode. So the Bootrom mode is a normally special hardware key combination when the phone is powered up, is powered off. So it's volume down or volume up. When you connect USB, you have to figure it out. It depends on the vendor which one it is. But for some vendors like Amazon, they've blocked booting using any keys, and then you have to short the eMMC, which means you have to short clock or data 0 line with ground on the start of the mobile, and then immediately you have to remove it, and then the device will enter the boot ROM. So the boot ROM actually can be easily detected. If you do a ls USB, you will see product ID of the USB port of 003, that's the boot ROM. And if you see the PID of 2000, it means it's the preloader. So that's pretty simple to distinguish where you are. And also you have to take care, because once you connect the USB to the phone, you only have about 2 seconds to talk to the preloader or to the boot ROM, otherwise it's going to go the next boot stage. So that's pretty critical for Windows if you use it, because you have to always use filter drivers in between, and sometimes you have to be very fast in order to install those filter drivers using ZDEC. Okay, so let's have a look at the encryption, because for some of you it might be interesting as well. So we've got several keymaster versions. Keymaster is actually a Google thing, which is it's the master of keys for the Android devices, and the old ones like Android 5 to I think 7 it was. They've got Keymaster version 1 to version 2, and it works pretty simple. So you've got Bootrom. From Bootrom, it's going to load the preloader, and the preloader it's going to pre-calculate the RPMB key. So if you have got rollback protection, it means that you have to get the RPMB key in order to write the RPMB. Reading the RPMB is normally no problem, except the RPMB itself is encrypted, which is the case for newer MTKs. And from there, the preloader is going to initialize the trust zone, and the trust zone is going to load the ARM trusted firmware, and the ARM trusted firmware combined with the trust zone, which could be anything like trust kernel, microtrust, trustzonic, whatever, they're deriving the keys. And with that keys, and combined with the user password, the metadata partition, which contains the encrypted key blob, is going to be decrypted, and with that decrypted key, which is called master key, you can decrypt the user data. It's normally encrypted using ESSV AS CBC. But that was in the past, because then Gal Benyamini attacked the keymaster, and I did as well, and Google learned from that. And then they made a new iteration, which is a lot tougher to break, and it's Keymaster version 3, and the actual version is Keymaster version 4. It works just the same way, and that's really specific for MTK. It's not the same for all MTK, and it's clearly not the same for the Qualcomm devices. So you've seen the thing is it's almost the same, except that the keys are being encrypted and are being stored encrypted in the RPMB, which is a pain actually, because you need to figure out how it's encrypted and you have to bypass all security. And the next step is to decrypt metadata, but you can't simply decrypt metadata, because on boot they do verify if the boot actually is having the right key. So if you're unlocked, or if you're having a wrong key, it means that the verified boot key doesn't match anymore, and that means that the user data cannot be decrypted anymore. So for that, it means you need to have the right public key in the boot, and you need to send it to the trust zone. Trust zone is going to say, yo, you've got a validated boot, you're allowed to decrypt the metadata, and then the metadata is being decrypted. And if you think, hey, that's going to be easy, well, even if you have the metadata key, deriving the user password, which means using a brute force attack for the user password, means it's very, very slow. So you've got 3 times of script, or 2 times of script and AES. It's going to take quite long to figure out user password if it's wrong. Okay, and so much for the full disk encryption. So in the past, the devices were full disk encrypted, but starting with Android 9, I think, the vendors are being pushed to use file-based encryption. And file-based encryption means not the full disk is encrypted, but just the file system. And for that, they're using instead encrypted extended 4 or encrypted F2FS. And that is divided into 2 areas, which is one is the device encryption, and the second is credential encryption. So device encryption is just for decrypting the device main area, which contains almost nothing, and the C area is where the user data actually is, and for that, of course, you need the user password. But even if, let's say, you've got your phone and your phone got smashed by some idiot, you won't be able to get your own data, even if you know the password and have everything, because of all those security mechanisms in between, which normal user can't bypass. So actually, you're clearly losing your data if you don't take care about your smartphone, which is a pain. Shouldn't be this way, in my opinion. Okay, so much for the introduction on MTK. Are there any questions? No questions. Okay. So let's go ahead and let's have a practical view on how to use those things. So I've got two smartphones which I prepared. One smartphone, a friend, he's in the chat, recommended it to me. So screw that, go and get your Gigaset GS290, and it's nice. So I haven't looked at it. I'm just going to write it into the chat. But today I'm going to have a look, and we'll see if it works as well. So expect some features, of course. But for the start, I'm going to use YumiDigi Power, which is a bit older. But it's pretty nice because it has UART on the PCB. So we'll be able to see UART as well. Which I've soldered onto the phone. And the first thing we're going to do is we're going to start and have a look at the MTK tool. You're able to get it over here. Just okay. So it's pretty similar to the way the Qualcomm EDL tool works. So you've got the option to print the partition table. The only nasty thing with the MTK is each time you run a command, you have to reboot the phone. That's just the way how it works, except for one command, which is stage, which I'm going to show, which is our own payload, of course. And then you've got the read commands to read partitions from flash, and the write command, erase command to get the metadata partition, which you could do as well using read command. We've got a reset command to reboot the phone. We've got dump prom. We're going to start with that one. We've got the payload, which is just the same as the MTK bypass tool. So it's going to load the payload you define. If you don't define any payload, it's going to use the generic bypass exploit, which means then all security will be disabled, and then you can do your own stuff, or you could start instead SP Flash tool in order to read and write flash without having any authentication. We've got the crash command, which is in some cases using, well, let's say some problematic commands. We are able to crash the preloader to get into Bootrom. It doesn't work all the time, so if you have the hardware combination to enter the Bootrom, use that one instead. The crash is just for, well, some devices like Amazon's. We've got the brute command. That's a command to guess the variable 1 in case you don't have it. So there's a config. I'm going to show that as well. But for most chipsets, we already have the variable 1, so you don't need to brute force it. The thing that's more interesting is the command get target config. Get target config means that it's going to show you the configuration of the device, the security configuration, and we've got p command, which actually is a bit of a hack. So in order to make it work, you need to have a patch preloader, and then you'll be able to read and write, but we don't actually need this one. we've got stage. Stage is much more powerful and will be much more convenient for doing any exploitation stuff. So I'm going to show that today as well. And there's a PL stage, which is just the same as stage, but stage needs to be run in Bootrom mode, whereas PL stage, as it says, needs to be run in preloader mode. Okay, so let's give it a go. I've prepared a phone, and the first thing we're going to try is to dump the Bootrom. So just going to start a command, and now the device needs to be powered off. And when it's powered off, you just press the, in my case, the volume down button and connect USB. And you can see on the left side the UART was printing out information. In case you wonder what's happening over here, it's because of the UART speed. So I'm going to show that as well. That's for the preloader. The Bootrom uses 100,000 1500, and just going to write it over here because it's easier. So for Bootrom it's this UART speed, and for preloader it's this speed. And then if you switch the baud rate, it's called, you can see the clear text for the preloader. So as you can see, we've dumped the Bootrom. So just to make sure that we really have dumped the Bootrom, because sometimes it's empty, we're just going to open it up. And as you can see over here, we've got some fancy EAs, which is typical opcode for ARM architecture, and it looks pretty good. So yes, that's clearly a Bootrom of MTK. So that's the ROM views code. Okay, so as we've got the Bootrom, I think how should we reverse engineer it? We just use Gitra for it, and we just import file and open the dumped prom file. And the Bootrom is normally always loaded at 0. For some devices it's a different offset, but let's say for 80% of the devices it's clearly this way, so it's 0. And we need to set the language, which is of course in this case ARM little. It's V7 or Cortex. I usually use Cortex. And we're just going to open it up, and we say yes, analyze please. We're not using the aggressive instruction finder, that's not really needed. And then you can see all those wonderful functions are going to sparkle up over here. And if not, you can still say please disassemble. And so on. So I'm not going too deep into the Bootrom. The only thing that it's important for reversing it is to find the command handler, which is somewhere around here normally. I don't know the offset right now, but I'm going to show you a neat way I've developed to find those functions that are interesting for us. So for that, I've coded a small tool. It's not yet published, but I will publish it. And then you say which Bootrom. You're going to start it, and it's going to derive all functions that are interesting, and also the watchdog, and also the variable one, which is needed for the Kamakiri exploit. and those functions like SPC, SLA, DLA. So just having a look at this function. So I think that was the SPC, yeah. So we're just going to call it SPC, and let's have a look. Obviously not everything has been decoded. Okay, let's have a look at the other ones. Or maybe let's have a direct look at the command handler. It's better. So on boot you've got the preloader in it, and in the preloader in it, it's going to initialize UART, and in the UART initialization, it's going to start the command handler. Yeah, it hasn't been disassembled, so we're going to do that now. And just give it a name, command handler. And over here you can clearly see the commands, which normally are being sent by the SP flash tool, for example. And if you're interested which command is going to run which, you can have a look in my MTK client source code, and over there it's in I think MTK Preloader, yeah, and over here you can see those commands and what they mean. So for example, the read command is D1, and the command to send DA is DA, funny. And we're going to have a look at the get target config, because over there the security is being verified. So it's DA, D8. So we know this one is get target config. And as you can see over here, there's the SPC. This one is normally the DAA, I think. SLA, DLA, no, it's SLA, and this one is DAA, and so on. So those functions actually read from the efuses, and the efuses say which protection is enabled. So in order to disable those protections, you have to attack the offsets, or to just remove the functions, or always return the right value. So you can see over here, this is the offset which is being attacked for the SLA, and you just set it to a specific value, and then the SLA is disabled. And you need to do the same for all efuses you can see over here. Okay, so much for the security of the Bootrom. Next thing we're going to have a look at is to read and write the flash, and to use the stage. So in order to read and write the flash, we need a dump of the preloader, and for that you need to have a copy of the preloader. So there are two ways to do that. The first one is go and grab a firmware where the preloader is included, and the second one is to dump it. Dumping isn't that simple, because you can't read without the preloader, because the DRAM config is missing. So in this case, we're going to use the stage using the query exploit, and we're going to start with the PL stage. Well, I'm not going to use the stage for the Bootrom, because in Bootrom you need to initialize the eMMC controller. For some devices we managed to do that using our own custom driver, but we haven't achieved it for all MTK devices so far. So in this case, it's just going to work in the PL stage. So we're going to start the PL stage. Yeah, I know. So we need to power off the device and then just connect. Don't press any button. You can see over here the preloader. Now I've changed the baud rate, and it's going to give you some insight into the target. So we see that in this case it's completely unfused. There's no security at all. We see the hardware code. We see that our custom payload has been sent to that offset. That's possible for all devices. You don't need any exploit as long as the security is disabled. So in case the security isn't disabled, it automatically tries to use command query to disable the security and then load the stage. So you don't have to care about that. Okay, so and now as we are on the stage, we can use the stage 2 script, and there are some commands that are possible. Keys is now reboot, so just ignore that one. And we are going to read for starter, let's say at the offset 0, 10 hex bytes, which is the start of the Bootrom. Oh, sorry. We need to define start and length. And then you can see that's just the code we had. So we are able to read the memory, we are able to write the memory, we are able to dump the RPMB, and what we wanted to achieve is to read the preloader. So we're going to start that, and as you can see, our eMMC driver is working, and it's going to dump the preloader. Okay, so the preloader has been stored over here, and the next thing we need to do is to reboot the device, and then to power it off again, and then we can use our MTK tool to read, for example, the metadata partition. And one special option is p-type, and p-type is very important because normally if you don't give that option, it just uses the regular eMMC, but you might be interested into special areas like boot 1 or boot 2. For example, to read the preloader, we just need to do preloader p-type is boot 1, and then just give it the preloader, which is in our case the preloader we dumped. But we don't need that, so we're interested into regular partition, which is metadata, which you could dump with SP flash tool as well. So I'm going to power off the device, disconnect USB, that's very important. And once the device has been powered off, we just okay. Oh yeah, of course. You need to give it a file name where it should be stored to, so we could just call it metadata.bin. Okay. And then just connect. And it should upload the stage, and it's going to read the metadata partition. So let's have a look. It should have the crypto footer, and as you can see, here we are. So easy peasy to read and write flash or to play around with MTK devices. What we haven't included yet is to jump into your own code in stage 2. So that is something that we will be enabling as well. But you already have read and write memory, and you can modify them as you wish. We haven't posted yet the source code for the generic exploit and the stages because, well, when we decide to release our payloads, they immediately have been integrated into unlocker boxes, and they said world first. But the problem was that those payloads we published didn't work as expected. They were just meant for development, and they just used it without knowing that, obviously, and they didn't give any credits. So people started to kill their phones, and well, that's a bad thing. So please, if you use open source code, do give credits. That would be really nice, and I think at least Chaos Master would be really thankful. Okay, so we've just downloaded the preloader, and let's have a look at how we can reverse engineer the preloader. And I already have for a plugin for EDA, because normally I use EDA all the time, but in this case we're going to do it manually using Jita. So we're going to open up the preloader. It's under logs. Yeah. So this is the header, and that's the preloader. We're going to give it again. No, it's a little. Yeah. Okay. Now the problem with binary snippets with Ghidra is you have to define the offset in advance. So normally I should do that over here, but I'm not doing it now, just in order to show you what you can do if it goes wrong. So we're just trying to open the preloader using offset 0, and that's clearly wrong, because you can see over here there's a header, and over here, which is called reserved whatever, that's the actual memory pointer where the image is starting. And over here, F0, that's the actual start of the preloader. Okay, so what we need to do is we need to use this address, and then we're just closing it. Maybe someone knows how it's easier to do that, but I saw that if you edit the segments, it's not going to work in Ghidra. So we're just going to reopen it. Oh, sorry, no, that was wrong. Just deleting it first, re-adding, and now under options, you really, oh, sorry, language, of course. Choose a little again, little. Let's take this one. Doesn't care. And now, very important, go to options, and there define the base address, which we just saw, which is 200F. Oh, good God. It's 1 minus. No problem, we can figure it out. Just open the preloader, and we've got the offset over here again, because copy and paste didn't work. 20OF10. 20OF10. Okay. Press OK and open it up. And now I can say analyze it now. And we know that the offset F0 is the start, which means you need to add to 200F10 exactly F0, which is 201000. And even though it starts with zeros, that's right. That's perfectly right. It's opcode that's working. So just press F12, and that's the start of the preloader. And as you can see over here, normally everything should be automatically disassembled, and if you search for text, for example, let's say USB, like jump DA. That's the easiest thing to find the command handle in the preloader. Just search for use BDL and then go backwards, and then you can see over here that's the command byte which is being used in the preloader, which is also used by SP-Flash tool. So you've got the commands in the Bootrom and you've got the commands in the preloader. Okay. Now that's a device which I already know that just works fine with my tool, and as promised I'm going to try the GS290, and well, let's see what we can do, or if we fail, if anything is there that has to be fixed. And we're starting just the same way as we did before. So we're going to dump the Bootrom, of course. Okay, the device is powered off. I'm going to press volume down, just starting with volume down, and then connect. And as you can see, it has just worked. The device model, it's the device before was the Umidigi Power, and the device now is the Gigaset GS290. One of those which was just lately in the press because they come pre-installed with rootkit or malware. So as you can see, we're able to dump the Bootrom. Let's verify if the Bootrom is fine. Oops, sorry. Let's have a look. Yes, looks good. So the next step will be to dump the preloader. So we're going to use PL stage. So we need to power off the device. It does take ages actually to power it off, but let's see. It's rebooting now. Okay. So it says successfully loaded stage 2. Let's try if stage 2 has been successful. Yes. So we're just dumping the preloader. Isn't that nice? And the nice feature of my tool is it's automatically renaming it to the original name, which is just deriving from the preloader itself. And we can have a look at the preloader. File could not be opened. Why is that? Ah, logs. Yeah. So looks pretty good. As you can see, preload has the same offset for loading the preloader, and it's also the same offset to start for the preloader, which is over here. And you can see the opcodes. Just pretty simple, pretty fine, nice. Okay, and the next step is to read, for example, the metadata partition, or we could read the boot partition if anyone needs the boot partition. And yeah, we just need to give it the preloader, of course. Disconnect first, and then power off the device. Sometimes it doesn't work for the first time. Okay, and it's reading boot. Yeah, thanks. It's a really nice toolkit. It has much more features. It's just a little problem with which I have published. We've got a really massive exploit toolkit which some parts of it will be publishing as well, but not for now. But you can do it already on your own with the stuff we have published. So as you can see over here, that's the boot image. Yeah. And what I had in the slides, which I forgot to mention, you've got two DA flash modes, and a newer one is called X-Flash, and that's also integrated. So you don't need the SP Flash tool from MTK. You can just use my tool to read and write the flash, and even on the protected ones, thanks to Kamakiri and Hashimoto. Okay, so I think that's pretty nice. That's cool because the Gigaset is a really nice device. It has malware on it, and the source code is available. So will be one of those devices which I'm going to add UART as well next time. Pretty nice. Okay. So of course I need to show you the security thing, right? So let's have a look over here for a device with security enabled. So the device I'm going to show is just a completely different one. It's called Hisense C30, and it has actually some protections enabled. Just let's have a look for the right cable. Okay. So here we are. So the first thing, of course, as we do usually, we try to dump the prom. So for that, device turned off and volume down, and as you can see, we got the prom as well. And over here you can see that SPC, secure boot, and the download agent authentication is enabled, which means you couldn't use normally SP Flash tool for doing anything, because you need to have the authenticated preloader. Okay, so let's give it a try if we can run our stage on it, right? Shall we? So PL stage we're going to try. I've never tried on this device, to be honest, because when I developed it, it was before I played around with that device. So we're going to start PL stage. Device is powered off. Can it bypass the partition encryption? Well, no. You can't bypass the partition encryption because the partition encryption is being handled in the preloader, and it's being handled in a trust zone. And I'm going to upload the slides which I presented, which clearly says, so it's not that easy to well, bypass the partition encryption. Not really. Except you mean to wipe the device, like erase flash, modify the boot partition, something. Yes, that's possible, because you disable secure boot chain. You could upload anything, so that's no problem. But to bypass or to unencrypt or something like that, that needs a bit more work. Okay, so device is powered off. Just going to connect it. And we can see up input output error. That's not good. Okay, that was unexpected. Okay, I know why. Yeah, that's a typical problem. Battery low. We're just going to try the Bootrom stage instead. Yes, you can do custom boot image because secure boot chain is disabled. So you can use anything. Yeah, so that's possible. Okay. So I think I need to do some more coding for this device. Doesn't look like it should work. Let's try to read boot instead. So the stage is not working, but it should work. So maybe I broke something for the older chipsets. I'm pretty sure I'm going to fix that very soon, because I can't stand bugs actually. So let's try to reboot, hopefully. He doesn't like me. Yeah. Do I have updates planned for Android Universal? Android Universal, that's for those who don't know what it is. Oops, sorry. That's a tool to automatically root the boot image. But for Android 10, the problem is that the boot image doesn't have a RAM disk anymore. So there might be ways actually to do it. For example, for the recovery. So yes, I'm going to dig into it, and I'm trying to support RAM disk routing on those devices as well. So that's on my to-do list. Yeah. And maybe I'm going to add it as well for MTK so that you can just load any boot image without having any signature. So to bypass the secure boot chain. Yeah. So as you can see over here, it clearly needs DRAM config for this DRAM. So you need to have a preloader. But as you can see over here as well, we successfully disabled the whole security. Okay, so if the stage would be working, which it doesn't right now, but it will be working, I promise, then you can dump the preloader, and then you can just use that preloader with preloader options to read. So anytime you are getting this message, it means you need the preloader. Yeah, so I think that actually concludes the MTK stuff, but I'm going to give you some small insight what we were doing, and maybe some cool hints what we're trying to do. So you know, for let's call it user convenience and for giving the best support to our customers, which means it's open source, right? We need to, well, let's say, have some kind of quality. So when we started with those payloads, we had massive issues with devices which we thought patching was working fine, but in fact, well, it didn't work fine. So what I'm going to show you is our quality management. I love that. It's just a management term. Sorry for that. So what I did is actually I wrote my own tool to emulate the preloader, and so we take over all those addresses which happen in the preloader, and we use Unicorn to actually emulate it, which is very neat because you can clearly see what's going on. And the same we did for the Bootrom, and I'm going to show you an example. So for the stage 1, for the targets, you can see over here the targets. The only thing we need is that configuration, but that's not needed because due to the generic payload, you don't need those offsets. And we've got, for all payloads, for all bootroms we are finding, we're doing validation. So those things we reverse engineer automatically, and then we emulate our own payloads to verify if the payloads work fine. So, and well, let's just show you how it works. So this one is going to test all Bootroms available, which we've dumped, against our payloads to prove that they are working fine. So it's going to compile it, and over here you can see it's emulating the Bootrom using our payload, and it's reading and writing memory, and it compares it automatically if the patching is the same way the security would work, which is a pretty neat thing. When I started, we had really grave issues, and with that, it's really simple. So once I get a new Bootrom, it takes just seconds to actually get the offsets and then to emulate it and to write the payload. But so far, I didn't have to write any payloads because the generic payload just works fine. We just had one single chipset, a very old chipset, which didn't work. And we've got the MT6580, which is also pretty old, which does work, but the stage doesn't work, and we don't know why. So we still have to figure out. So there are some few things which we need to do. Okay, so there's another question in the chat. When you have disabled security, how do you continue the boot process with an, for example, modified boot image? It's pretty simple. So the only thing you need to do is just write your boot image to the flash and then disable security, and then it will work because you've bypassed the RSA security. Pretty simple as that. You don't need to, you can modify anything. You can modify trust zone, whatever you want. Okay, that's a large question. So I'm going to read that in a second. So as you can see over here, all tests passed, emulation done. So that's what we call quality management, right? So that is something that I wanted to show. And the stage 2 source code, as you can see over here, is really massive. We haven't published it because it took a long time to reverse engineer the MMC driver, and I had to emulate the MMC driver as well. So it will take some time until we fix things, and once everything is fixed, I think we will be open to release the code as well. Okay, so let's try to read that long question. Okay, so if you unlock the bootloader, it means that the root of trust doesn't work anymore. So if you are modifying the boot image, then you would need to also patch. Let me show you something. I think it's just the same for the Qualcomms. So I've written a paper on that stuff, which explains it a lot better than I could right now. Oh, sorry, it's slides. So this will be the same for the MTK stuff, which I was just giving at the start of the stream. So there's one which is called Qualcomm Crypto. And if you have a look, let me see. Yeah. So over here it's a bit more clear to see. The problem is the root of trust. The root of trust is the verified boot key, which is generated by the public key hash, which is at the end of the signed boot or in the VB meta file or VB meta partition. So if you change the boot, of course the signature won't match, and then you can't decrypt the data, and then it wants to factory reset because the encryption key doesn't work anymore. So if you get the orange state, it means that the encryption key is being set to 0, and that means you need to wipe the device. That's fine if you want to do development stuff, but if you're some guy, let's say from forensics, of course this won't work. So then you would need to patch all parts in the chain, which means the trust zone, the boot, the A boot, in order to send the right public key hash, and then it should work. And of course, no flasher boxes support that because they are just there to flash or to repair devices, right? Okay. Good. So much for the question. Yeah, no problem. I haven't published them yet. Just kidding. Yeah, have a try to use enable JTAG. Well, that's a good question. There's a MTK debug board, and it can be used to do some JTAGing on the MTK, but the problem is that this board is not being sold to private persons or to companies. So I already asked some friends in China, but they also didn't get it. So I had to do a board for this connector, and let me see, maybe I've got it in KiCad. I haven't got it on this PC, sorry. So I've made a project. I've manufactured a PCB board to do the JTAGing, and that's one of the next things I'm going to do, pretty sure. But it should be very simple using that PCB and then using FTDI board. I think writing the open JTAG configuration shouldn't be a big issue because MTK is pretty standard. It's not like Qualcomm that use some specific or special JTAG ETM configurations. Yeah, that's right. So okay, so one of those things we're still having with the stage is we can't patch the preloader and then run it from stage. We think that's a problem of memory caching or the decache. So if anyone has any hint or thinks he could help us, you're pretty welcome to do that. In our case, if you try to, or if you want to patch the preloader, you have to fix the preloader itself because the preloader has hashes. So either you recalculate those hashes or you fix the checks, and then you can just use send DA. So using Kamakiri, you disable the security, then you can use your patched preloader, but it only works right now if you use send DA. That's just one of those things I wanted to mention. And I think, well, we're pretty done for today. Do you have any more questions? I know it's has been pretty intense and I couldn't show everything, but we're already 1 hour away from our start, so I have to finish. Do you have any questions? Tick tock, tick tock, tick tock. No? Okay, so then just thank you for watching and see you next time. Next time we'll be giving some presentation on, let's say, Qualcomm 5G modems and how to route them, maybe. So have a nice evening and enjoy reverse engineering and stay safe. Goodbye.